Okay, so we'll get back to the notes here. In problem 4, we want to find the future value of a $3,300 deposit at 3% for 2 years if the account pays interest compounded quarterly. Okay, so here is the formula that we're going to be using. A equals P times 1 plus R over N to the NT power. Okay, and that's just the general formula for when you're compounding a finite number of times. Now we also have compounding continuously, which is where you're using what's called the PERT equation. Okay, A equals P times E to the RT. We'll look at some examples of that coming up here. But so I'm compounding quarterly, so that means that N is 4. Okay, so 4 times in the year, I'm going to gain additional money on top of the money that I've already made. The P value is $3,300. Okay, so that's how much I'm investing. And I'm multiplying that by 1 plus R is 3%, so as a decimal, that'd be 0.03. And then I'm going to raise that to the power 4, N is 4, times 2. T is 2. Okay. T is the time in years. R is the rate. N is the number of times that you're compounding in a year. And P is the present value. Okay, so then the next thing that I'm going to do is I'm going to go ahead and type in 1 plus 0.03 divided by 4. And from that, we have 1.0075. Okay, and I'm going to raise that number to the 8th power and then multiply that by 3,300. Okay, so let's go ahead and raise that to the 8th power and then multiply that by 3,300. Okay, so this is what I end up getting there. And now, by the way, you're working with money, so always go to the nearest cent for rounding purposes. So it looks like in 2 years, if I just let the money sit there and do its thing, I should have $3,503.28. Okay? Now, be careful about rounding anything. I wouldn't round anything until the very end when you go near a cent. Okay, like, for example, if we type in 1 plus 0.03 divided by 4, we did that, and we call it 1.01 to the 8th power, then we're probably going to be pennies off. Okay, you have to think, if this is your money, would you be happy if they're pennies off? You know, or in some cases, like, you might not be pennies off, but you might be hundreds of dollars off. Okay, like, would you be happy about that? No. So I you know, for these problems, I want the answer to the nearest cent. If you're a penny off, I'm taking a point off. Okay? And now that shouldn't be a harsh thing because, again, you got to think about if this is your money. You know, you're not going to want someone to always be pennies off, or in some cases you could be hundreds of dollars off, depending on how far you round. Okay? So I wouldn't round anything until the very end when you round to the nearest cent. If you do it like that, you're never going to be pennies off. Okay? Let's see. Let's take a look at problem 5 next. It says the population of Nevada in millions can be approximated by the function p of x equals 3.1 times e to the power 0.014 times x, where x represents the number of years after 2020. What will the population of Nevada be in 2035? Okay, so x is the number of years after 2020. So if I want to know the population of this state in 2035, it would have been 15 years after 2020. So all I'm going to do here is plug in 15 and then simplify this. Okay, So let's go ahead and do that. In the power, if I type in 0.014 times 15, I'm getting 0.21. Okay, so then type in e to the power 0.21. Here's e to the power 0.21. And that's what we get. Okay, and then I'm multiplying that by 3.1, it looks like. Okay, so times 3.1, and that's what I'm getting. Okay, so it looks like if this state continues to grow at the rate that it's been growing at, then in 15 years, in the year 2035, it would be at 3.82 million people. Okay, make sure you got the units there. Okay, there's not roughly 3 people in the state of Nevada, right? So 3.82 million people. Okay. Let's take a look at problem 6 next. So in problem 6, it says the body temperature in degrees Fahrenheit of a person who was found dead in an apartment that maintained a constant temperature of 75 degrees Fahrenheit can be approximated by the function f of t equals 75 plus 12 times e to the power negative 0.206 times t, where t equals 0 corresponds to the time that the body was found. Okay, what is the body's temperature 6 hours after it was found? All right, well, t is the time. Okay, so if I want to know the temperature of this person 6 hours after it was found, then t would be 6. Okay, so I'm going to go ahead and plug in 6 into this function here. I got 75 plus 12 times e to the power negative 0.206 times 6. And let's go ahead and simplify that. So negative 0.206 times 6 is negative 1.26. That's what I'm getting there. Okay, so then I need to raise e to the power negative 1.236, and then hit enter. Okay, and we are going to multiply that by 12 and then add 75. Okay, so then times 12 plus 75. And so here's what we're getting. So it looks like the temperature of this person 6 hours after the person was found is 78.5 degrees Fahrenheit. Okay. Now, here's an example of exponential growth. So the population of the state is getting bigger over time. And here's an example of population decay. So as time goes on, the temperature of the person is gonna drop. Okay, which is indicated by the negative exponent. Okay, so if the exponent is ever a negative, that means that you have exponential decay. And if the exponent is a positive, like it was up here, then you've got exponential growth. Okay, we're going to talk a lot about exponential growth and decay models like kind of at the end of this chapter here. Okay. So, for this problem, include the units, so just so it's not to be confused with the degrees Celsius or kelvins or something like that. Okay, so 78.5 degrees Fahrenheit is the body temperature of this person. Problem 7 says to consider the graphs of f of x equal 3 to the x and g of x equal log base 3 of x. Complete the table below and then use these points to sketch the graphs of f and g. Draw the line y equals x to illustrate that the graph is of an inverse is a reflection across this line. Okay, so we're going to go ahead and graph y equals 3 to the x first. And we're using these values in this table. So if x is negative 2, let's see, 3 to the negative second power, that'd be the same as 1 over 3 squared, or 1/9. Okay, so the point negative 2, 1/9, that'd be on the graph there, that's right there. If x is negative 1, 3 to the negative first power is 1/3. Okay, so negative 1, 1/3, that point would be on the graph. If x is 0, anything to the 0 power is always 1. Okay, so this curve, just like any other basic exponential, y equals a to the x, will always cross to the y-axis at 0, 1. That will always happen. Okay, so here's 0, 1. Now if x is 1, 3 to the first power is 3, so 1, 3 is on the graph. And if x is 2, 3 squared is 9, so 2, 9, that point is on the graph there. Okay, and then I can draw this curve. So here's the graph of y equals 3 to the x, right? And an exponential function always has a horizontal asymptote on the graph. So this one is going to be at y equals 0. So I'll go ahead and make a dotted line at y equals 0 there. And, you know, because x can be positive or negative or 0, it does not matter. You'll never have a negative coming out of this. You'll also never have 0 coming out of this. Okay, so this curve is going to get closer and closer to the x-axis there on the left, but it's never going to get there. Okay, so that'd be the graph of y equals 3 to the x. Now, any exponential is always a one-to-one function. One-to-one, we got to go back to chapter 1 for that. That just means that I flip x and y. Okay, so I'd have the equation x equals 3 to the y. Now, x equals 3 to the y means y equals log base 3 of x. So if I want to graph y equals log base 3 of x, I do, I need to graph the inverse of y equals 3 to the x. So all I got to do is switch the coordinates on these points and plot those new points. Okay, let's go ahead and do that. So negative 2, 1/9, that's going to be at 1/9 negative 2 right there. Negative 1, 1/3 is going to be at 1/3 negative 1, that's right there. Here's 0, 1, that's going to be at 1, 0. 1, 3 is going to be at 3, 1. Okay, and then 2, 9 is going to be at 9, 2. Okay, and then using those points, I can go ahead and draw this curve. Now, the x and y coordinates just got switched. Okay, I had a horizontal asymptote on the graph of this exponential. That's going to turn into a vertical asymptote on the graph of the logarithm. Okay, so x equals 0, there'd be a dotted line there, and this graph is going to get closer and closer to the y-axis there. It's never going to get there, though. Okay, so this graph would be, you know, just a quick rough sketch of the graph of this logarithm here. Okay, now whenever I graph a function and its inverse on the same picture, like I've done, those two curves will always be symmetric to the line y equals x. That will always happen. Okay, so here's this line y equals x. Now, to get the graph of the logarithm, all I did was I took the graph of this exponential, y equals 3 to the x, and I rotated it about the diagonal line. Okay, by doing that, I end up getting the graph of this logarithm here. Okay, and that would be how you graph any logarithm. Okay, you're going to have to first know the corresponding exponential, and then flip all the coordinates, and then plot those new points to get the graph of the logarithm there. Okay, so if I want to graph y equals log base 5 of x, I'll have to know what the graph of y equals 5 to the x is, and then switch all the coordinates, And then I got that graph of y equals log base 5 of x. Okay. So, you know, in math books, like you have to know what inverses are in order to do anything with logarithms, right? Because a logarithm is the inverse of an exponential. You also have to know what an exponential is to do anything with logarithms, right? Because a logarithm is the inverse of an exponential. Okay, so in every math book that you'll ever see, you'll see inverses and exponentials being described before they talk about logarithms there. Okay. All right, why don't we go ahead and stop the video right there, and I'll pick up with problem number 8 in the next one there.